Alright guys, let's get started with today's video. We're just going to cover this section 5.2. It's really all I want to try and cover today over a video. If you're keeping up with your page numbers, again, like I said, these sections 5.1 and 5.2, they're off. This section 5.2, it starts on page 66. Alright. So in class on Tuesday, we finished up talking about section 5.1, which was what we just kind of generally called our introduction to structures. Okay, we talked about the different types of beams, different types of supports, the different types of loads, point loads, uniform loads, triangle loads, trapezoid loads. We talked about pin supports, roller supports, fixed supports. Talked about the reactions that they generate. Did a little bit of introduction to, beams, columns, trusses, and frames. All of these different things that we just kind of need to have a general idea of to be able to start analyzing these structures and looking at these things from a structural engineering standpoint. One more thing that we need to talk about, though, is how to work with distributed loads themselves. We talked about distributed loads of what they are, on Tuesday, but now we need to kind of figure out how to work with them a little bit. It's not complicated, but it's just something that we need to figure out. So these distributed loads that we have on our beams, let's just draw one real quick. So maybe we have this simple beam, okay, and say it's got some type of load, and I'm just drawing a generic functional load, right? So this functional load, W of X, has got some length that I'm going to call LW for length of the distributed load W, right? So LW is the length of the load. Does not necessarily correspond to the length of the beam, right? The beam could only be partially loaded with this distributed load. A lot of times what we're looking for is to break this force, this distributed load. Let's just break it down into one single point load to make our life easier, okay? And the way that we do that, I want to take this load, and instead of having a distributed load on the beam, I just want to replace it with one single point load somewhere along this beam, such that it all comes out to be basically the same loading. It has the same effect on the beam as it would being a distributed load, right? So replacing a distributed load with a single point load. That's what we're trying to get out of this section 5.2, is coming up with what we call the resultant force of a distributed load. To be able to do this, we've got to have two things, right? We've got to figure out two things. First, we got to figure out what the magnitude of this resultant force is, right? So if I've got, let's do a simple example, okay? Maybe I've got a distributed load that is 100 pounds per foot, right? So you can imagine every foot along the length of a beam, you have 100 pounds. Okay, so 100 pounds per foot distributed load, and say that load is 10 feet long, okay? 100 pounds per foot for 10 foot, total load is 1,000 pounds, right? 100 times 10. That's pretty easy to visualize for a uniform load, right? That makes sense. If maybe it's not a uniform load, maybe it's a trapezoid load or a triangle load, or even a functional load, right, where our load has to be described with some function in terms of X. Well, how do we figure out how much the load is? The answer is that the magnitude of that resultant force is just simply the integral of the load, right? The area of the load itself becomes the magnitude of the resultant force, right? So we can write this such that the magnitude of this resultant force Fr is just equal to the integral from 0 to LW of W of x dx, right? If I can write dx properly, there we go. That's it, right? So just integrate the load. The area of the load becomes the magnitude of the resultant force, right? The second thing that we need to do is figure out the location of this resultant force, right? So I was looking back at this little picture that we drew. This W of x has got some length of LW, right? The magnitude of this FR, the magnitude of our resultant force, comes from just integrating the load itself, right? Just finding the area under the curve tells us how many pounds or how many newtons that load is, right? Total. The second part is trying to figure out this location x. Where do I put this load such that it has the same effect as the distributed load did originally, right? We do this by simply taking a moment and setting it equal to 0, okay? So let's take a look. Sorry. So let's take a look at our distributed load itself. Let's pluck that load out and let's make it bigger. Let's explode it up, okay? All right, so if this is W of x, right? I'm going to say our x-axis is here, and our w-axis is vertical. This will be the point O. This is the origin. We know that the area underneath that W of x curve is equal to the magnitude of FR, right? Also, FR is somewhere here. Okay, this blue line is the resultant FR. That resultant FR, we're going to say acts at some point that we call X bar, okay? I'm actually going to redraw this real quick, guys, to where I have some room below, okay? Alright, so FR acts at some distance X bar from the origin. What we're trying to do is set the moment of these two separate loads, the moment of the distributed load about O and the moment of FR about O. We need those to be equal to each other, okay? So if I take these moments, the moment about point O from FR is just FR times X bar, right? Everybody agree with that? You should. Okay, we're going to set that moment equal to the moment from the distributed load about point O. Well, the moment from the distributed load about point O becomes just a little bit more complicated to understand, right? So we have to put it in integral form. What we're going to essentially do is imagine a vertical strip, and we're going to integrate it horizontally. So you may go back to Calc 2 or something right here with these integration strips, right? I'm going to say that this integration strip is X. You know, I'm going to idealize it as a rectangle that has width of dx and a height of w, okay? A height of w of x. Whatever w of x is, that would be the height of this rectangle. And then this rectangle, this integration strip, has a width of dx. And that, we're going to imagine we're doing an infinite number of these rectangles from 0 to L sub w, all right? To take the moment of this strip about 0.0, we just need to know the area of the strip times x, right? So the area of the strip is w of x times dx. That's the area of the strip, and then take it, multiply it by its moment arm of x to get the moment about 0.0. So w of x dx is the area, which is the force. That force, w of x times dx, gets multiplied by x to get that moment. All right, so x times w of x times dx, that's the moment about 0.0 of the little bitty strip, and we're going to imagine we've got all these little strips from 0 to L sub w, so those become the bounds on the integration. So 0 to L sub w, x, w of x times dx. Okay, so the location then, just solving for x bar from this equation that we've just come up with, x bar is just equal to 1 over fr. We're just moving the magnitude over to the other side. 0 to L sub w of x, w of x dx. Okay. The hard part here is just coming up with what w of x is, right? We need to figure out what this term is. And once we have that, all the integrations will become easy. And it'll just be numbers from there, okay? So let's just talk about our first example then. Let's just go to the first example. It will start making a lot more sense after this. So let's determine the magnitude and the location of the resultant force for a uniformly distributed load with length of L and a magnitude of W, okay? So essentially, just a plain Jane uniform load. It's got a magnitude of W, could be, 5 kips per foot or 30 kilonewtons per meter, doesn't matter, right? And it has some length. The length of this load is some length L, okay? Let's replace this load with a single point load and figure out where that point load needs to be in order to have the same effect as this distributed load, right? So step 1, magnitude of the load, Fr, is just equal to 0 to L of W of x dx, right? That's what we said from our previous page, right? F of r, magnitude Fr is just integral of W of x dx. The hard part is just figuring out what the W of x is. For a distributed load, W is constant, right? It does not matter where you are along the length of that load. W is just W. At the beginning of the load, W is W. At the end of the load, W is W. It doesn't matter, right? 10 pounds per foot, 100 kips per inch, doesn't matter. It's constant, right? So W of x just equals W, and it's a constant for this problem. So what do we do with constants and integrals? We just pull them out, correct? So this becomes the integral from 0 to L. I'm sorry, I need to pull the W out. Of dx. That's all it is, right? So integral of dx is just x, right? We take x, we evaluate that from 0 to L. What does this tell us when we evaluate this? It tells us that the magnitude of Fr just is W times L, right? And let's just look at this critically. Does that make sense? I hope it does, right? So if we've got a magnitude W and a length of L, the total load from that distributed load is just W times L, right? So let's put some numbers on this to make it make sense. If W is 100 pounds per foot and L is 10 feet, we know you've got 100 pounds per foot for 10 foot. That's 1,000 pounds. That's just W times L. That should make sense. And we've just proved it mathematically through our integrations, okay? The next thing we need to figure out is where do we put the resultant load so that it does the same thing? Where can we put it such that it has the same effect as the distributed load? So x bar is equal to 1 over fr times integral of x, w of x, dx, right? 0 to L on the integration. We've already figured out what fr is, correct? Fr is just w times L. And we know that w of x is just w, it's just a constant. So what we find here is that we can pull that constant w out. We'll have w over wl for fr integrated from 0 to L of x dx, right? All of that cancels out. The w's do. We just get 1 over L times the integration of x dx is just x squared over 2. I'm sorry. 1 over L times x squared over 2. Evaluate that from 0 to L. What we find is that we get L over 2 minus 0. So x bar just equals L over 2. Again, let's just take a step back from this now and ask ourselves, does that make sense? If I've got 100 pounds per foot for 10 foot, we know that the total load there is 1,000 pounds, right? Well, if our load is uniformly distributed, does it not make sense that the resultant load would just act right in the middle? That's the same thing, right? We got 100 pounds per foot for 10 foot, or we can have 1,000 pounds acting at 5 foot over, right? Because that would be in the middle of our 10-foot load, right? Mathematically, what we've just proven is that the resultant of all uniform loads, the magnitude is just W times L, and the resultant force will always act in the middle. All right, this is how we deal with uniform loads. We just figure out what the total load is, and then we place that resultant right in the middle of that uniform load. Okay, hopefully that instinctively makes sense, and hopefully you followed along here where we just proved it mathematically. All right, let's do another one real quick, but instead of a uniform load, let's look at our other very common load of a triangle load. Okay, so this time, let's go back to Fred. This time we've got a triangular load that the intensity of the triangle load, the height of it, if you will, is W. Out here at the tall end, it would be 0 on the left side. And again, we have some length L to this load. This time W is not constant, right? So this line becomes W of X, right? So it's not constant. At the left end, W is 0. At the right end, W of X is W, right? So W of X is not constant along the length. So we have to formulate an equation, right? So it's just a line, though. It's a simple equation. It's just a line. So if I have this be my x-axis, this be my w-axis, right? This is point O. My W of X, then, is simply rise over run plus some y-intercept, right? So rise is W, run is L, times X, plus the y-intercept, which is 0, right? So our W of X function is now just W over L times X. You can plug in any number for X from 0 to L, and it will tell you what the magnitude of that load is at that point, okay? So let's plug this in into our equation, right, where we're just going to integrate from 0 to L of W of X dx to get the magnitude of the resultant force, okay? So W of X is W over L times X. W is a constant variable. The only variable that we have is X itself, okay? So what we have is magnitude of FR is equal to W over L integral 0 to L of X dx. All right. Again, just reducing this down, magnitude of FR then just becomes W over L. Integral of x is just x squared over 2. Evaluate that from 0 to L. And what we find then is that our magnitude of FR is simply 1/2 W times L. Okay? Again, let's just take a step back. Look at this big picture. Does that make sense? If we take a look back up here at our uniform load, the area was just, I'm sorry, the magnitude of the resultant load was just W times L. We've come to understand that the magnitude of our load is just the area of our load. So let's look at our triangle. What's the general equation for area of a triangle? It's just 1/2 base times height, correct? So if my triangle here has a height of W and a length of L, 1/2 times W times L should be the area of that triangle, which is the magnitude of the resultant load. And again, once more, we just proved it mathematically, right? The magnitude of this load is 1/2 WL. We proved it with our integrations. The question this time, though, that should all be making pretty good sense. The question, though, this time is, where does the resultant load of this triangle load act? Where can I put that single point load such that it has the same static effect as the triangle load itself? This is where we're going to have to do an integration, right? Because it's not just in the middle, right? Because the middle of a rectangle is the middle, but the middle of the triangle is not going to be the middle of the triangle, right? The centroid, or kind of that central location of a triangle, is not just going to be L over 2. It's going to be shoved off to that right side like we've drawn it, because you've got more load on the right side than you do on the left. We've kind of got to find some type of what I want to call a balancing point such that FR will have the same effect, right? So let's look at this from our mathematics standpoint of our integrations. X bar is 1 over magnitude FR, integral 0 to L, x, W of x, dx, right? Sorry guys, my pen is kind of acting up. X times dx. Okay. We've already figured out what the magnitude of FR is, right? It's WL over 2. X is just a variable. W of x, we already know what it is. It's W over L times x. All we've got to do here is just plug and chug on the integral. Okay, so 1 over FR, which is WL over 2, right? So I'm actually just going to put that 2 on top. So I'm going to have 2 over WL times the integral 0 to L of x times W of x, which is W over L times x dx. We can pull W and L out, so we get 2 over L squared times the integral from 0 to L of x squared, right? That's just x cubed over 3 though, correct? Evaluate that 0 to L. And what we find here then is that x bar equals 2/3 of L. Okay? So for all triangular loads, the magnitude of that resultant is just 1/2 times W times L, right? It's just the area of the triangle. That's how much the total load is. 1/2 times W times L. The location of that resultant force is 2/3 the distance L from the small end, or if you want to think about it the other way around, coming from the right, it is going to be 1/3 L from the tall end. Okay, from the big end. This is always for triangular loads, right? These examples that we've just done are the two most common types of loads that we have: rectangle loads or uniform loads, and these triangle loads, right? These linear loads. What we've done here is mathematically proven what the magnitude of the resultant is and where those resultants act. So it doesn't matter what the numbers are, right? Every single rectangular load, the magnitude is W times L. The location is right in the middle, L over 2. For triangle loads, the magnitude is 1/2 times W times L, right? It's just area of a triangle. And then the location of that resultant is 2/3 L from the small end, or 1/3 L from the big end. Okay? This is always what it will be. The next example on page 68, it would be, I guess. I wanted you to do the same thing to figure out what the magnitude of FR and what X bar would be for a trapezoidal load that's got a starting value of W1 and an ending value of W2, and the length of it is L, right? You do the same thing. We'd come up with some W of X equals something, W2 minus W1 over L times X plus W1, etc., etc. You'll figure up all these different things, go through the integrations, but what ultimately happens is you get an equation that's not very easy to remember, and there's no need to remember it. Instead of trying to analyze trapezoid loads as trapezoid loads, what I want you guys to do always when you see a trapezoid load is to break it down into two separate loads, such that we have a triangle load on top and a rectangular or a uniform load on the bottom, right? So let's just make that note. I'm not going to go through the math on this. If you're interested in seeing the math on this, just email me. I'll send you the stuff. But just always treat trapezoid loads as a triangle load with a uniform load. Just break it into two. If you can do that, it'll all work out. It'll work out the same thing, the same exact way. Just treat it as two separate loads. Okay. So that's it. That's basically all I wanted you to know is rectangle loads and triangle loads. But I feel like I wouldn't be doing you guys justice if we didn't do at least one example with some numbers in it of maybe something just a little bit more complicated. So let's imagine we have this load, okay? I've got some functional load, W of X, okay? We'll just go ahead and set that as 0, or as the origin, right? The vertical axis will be W, horizontal axis be X, right? W of X is given to us in the problem statement. W of X is equal to negative 2x squared plus 4x plus 16. Okay. The load itself is 4 foot long. What I want to know is, how do I replace this functional load with a single point load, and where do I need to put that single point load so that it has the same effect as the distributed load, right? So let's just do it. And there's nothing different on this problem than we have done any of the other ones. We just have numbers this time. instead of variables. Okay, so magnitude of FR, again, it's just the area under the curve. So 0 to L sub W of W of X dx. This time our integral is 0 to L sub W. L sub W is 4, right? That's the length of the load, right? 4 feet. W of X is negative 2x squared plus 4x plus 16, right? dx. This is just basic Calc 2, right? This is just evaluating an integral. We get negative 2x cubed over 3 plus 2x squared plus 16x. Evaluate that from 0 to 4, right? This tells us that the magnitude of FR becomes 53.33 pounds. Okay, so that's the total load of this of this functional load. The total load is 53.33 pounds. Now the question is, where do I put this 53.33 pound load such that it has the same effect as the distributed load? Again, it's no different, just plugging and chugging into the equations. X bar is equal to 1 over FR integral 0 to L sub W of X times W of X dx. So again, just plugging these numbers in, we get 1 over 53.33 integral 0 to 4 of X times negative 2x squared plus 4x plus 16 dx, right? I'm trying to scroll down. What this comes out to be is negative 1, or I'm sorry, not negative, just positive. 1 over 53.33 of negative x to the 4th over 2 plus 4x cubed over 3 plus 8 plus 8x squared on the last term. Evaluate that 0 to 4. X bar comes out to be 1.6 feet. So putting that up here on the diagram then, this distance is 1.6 feet. You take that 53.33 pound concentrated load, put it at 1.6 feet from the left, because that's where our bounds of integration are coming from. They're going left to right. 0 to 4, right? That's going left to right. Put that load right there. It's going to have the same static effect as the distributed load, right? So you can take this functional load, do this trick with it, right? Come up with a single point load. From here on out, everything will become a whole lot easier. So that's it. That's the magnitude of FR. That's the location of it. The last little bit here, the example asks for what is the maximum intensity of this distributed load, right? Because we can look at the distributed load, W of X, and find out what the intensity of it is at the beginning, right? We just plug in X equals 0 into it. So we plug in X equals 0 into W of X. We find that the intensity of the load at the beginning is 16 pounds per foot. Right, negative 2x squared plus 4x plus 16 when x is equal to 0 becomes 16 pounds per foot. If we put 4 into it, W is equal to 0 at x equals 4, but somewhere in the middle it goes up, right? I need to figure out what the maximum value is. I want to know what the maximum value of this distributed load is. And how do we do that? I'm just trying to figure out what that maximum value is, and I've got the function. I just want you guys to critically think about this. You know what? I think I'm going to make this, well, no, I was going to put this in as your homework problem, but I've already made up the homework and posted it to iLearn. Let's just do it. It's just simply the derivation of W of X, right? You just take the derivative, because the derivative is going to be the max or min, right? That's what a derivative is. It's the change in slope, right? Take the derivative, set it equal to 0, and solve for it. So part 2, all right, all of this was part 1. All of this was part 1 for, call it resultant load or something. Part 2, we'll just call it like max W. Trying to figure out what the maximum intensity of W is for this problem. All we do is take that derivative, set it equal to 0, and solve for that location, right? So we know what W is. Let's just take dW dx. So derivative of W with respect to x, right? We just get, scrolling up, we'll get negative 4x plus 4, right? That's it. Negative 4x plus 4, right? Set that equal to 0. Solve for it. So dW dx equals 0. When we solve for that, x must equal 1 foot, right? So the maximum location is at 1 feet, is at 1 foot from the left end. But that doesn't tell me what the maximum W is. All we have to do now is plug in that 1 foot back into W of x to figure out what that maximum function is. So you just put in W of 1. So we get negative 2 times 1 squared plus 4 times 1 plus 16. And what we find out then is that our maximum intensity here is 18 pounds per foot. Use some critical thinking there to figure that one out. All right. That's really all I want to cover in a video. Our next section in the notes, we're going to move on to section 6. Right? We're going to start talking about equilibrium of a rigid body. You know, in section 4 of the notes, we talked about equilibrium of a point when we did 2D and 3D equilibrium of the point. Moving forward, we're going to be looking at 2D and 3D equilibrium of a rigid body. Those are section 6.1 and 6.2 respectively, right? I really don't want to cover any of that stuff in a video. It's something that I feel like we need to talk about in class. You need to be able to ask questions and have things explained in person. So this is really all I want to cover in the video, with the main points, right? Going back to this, I can't drill it enough to you. This is the main point of this whole section 5.2. The magnitude of the resultant, right? The total load of a uniform load is just W times L, and it acts right in the middle of the uniform load. For the triangle load, the total load is 1/2 W times L, and it acts 2/3 L from the small end, or 1/3 L from the larger end. Okay, those were the key takeaways for this section. All right, with that being said, I assigned a homework on iLearn. It's due Thursday, October 13th when we come back for class, because October 11th is fall break. We will not have class on October 11th. So I will see you on October 13th. We'll start talking about equilibrium of a rigid body, and that homework is due on that day as well. All right, see you then.